Here is a question on general organic chemistry. Read the question carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Resonance stability is enhanced when charge separation leads to aromatic systems. The parent molecule consists of a 2H pyrene ring, 6-membered ring with O and to C is equal to C bonds, fused connected via a single bond at C2 to a cyclopentadiene ring. Moving on to the next step. Identify the connectivity. The molecule has a 2H pyrene type ring connected through an sp3-like carbon to a cyclopentadiene. The key resonance involves moving electrons from the C to C bond connecting the two rings. Moving on to the next step. Evaluate aromaticity in canonical structures. If the lone pair or pi electrons are shifted such that the cyclopentadienyl ring gains a negative charge, 6 pi electrons, 4n plus 2 with n is equal to 1, it becomes the aromatic cyclopentadienyl anion, very stable, 6 pi electrons. Simultaneously, the oxygen-containing ring loses electrons from the junction carbon and oxygen bears a positive charge, making the beryllium-like cation, also aromatic, 6 pi electrons in the ring including O with positive charge. And for the final step. Option B shows O with a positive charge, O+, in the 6-membered ring and a negative charge on the cyclopentadienyl carbon, junction carbon, giving a cyclopentadienyl anion. The beryllium cation, O+, in 6-membered ring with full conjugation, is aromatic, 6 pi electrons, and the cyclopentadienyl anion is also aromatic, 6 pi electrons. Both rings are simultaneously aromatic. Option A negative on C of pyrene ring and positive on O, but the cyclopentadiene ring is neutral, only one ring gains aromaticity benefit, and placing negative charge on sp2 carbon of pyrene is less favorable. Option C cyclopentadienyl cation, positive on junction carbon, has 4 pi electrons, anti-aromatic, very unstable. Option D positive charge on junction carbon of cyclopentadiene again suggests anti-aromatic cyclopentadienyl cation, highly unstable. Option B gives the maximum stabilization through double aromaticity, beryllium cation, aromatic 6 pi, and cyclopentadienyl anion, aromatic 6 pi, making it the most stable canonical structure. Therefore, the correct answer is B. Therefore, the correct answer is option B.